All right, I will talk about the preliminary interpretation of the Southwest-1 line, largely focusing on the Archean history and suggest some possible correlations with the Midwest-2 line. And then I'll briefly touch on the Proterozoic modifications of the Julian Craton's margin, but mostly as an introduction to the next talk. That will be Ivan talking about the Proterozoic. So this is just to reiterate what Fiona showed in her talk as well, that there are common aims that are common to all the three lines, which is largely mapping the crustal architecture of the West Julian Craton, and as we move west, the Proterozoic, the nature of the Proterozoic and Phanerozoic modifications of the margin, as well as the architecture of the Perth Basin. For the Southwest-1 line, the Southwest-1 line was specifically designed to test some of the major outcomes of the 2021 AGP map that we produced for the Southwest, including testing this new terrain boundary that we proposed. You've seen that we've moved the boundary by about 200 kilometers southwestwards from its previous location, shown by the dashed line, into this new location here, shown by the solid red line. During this mapping, we've also identified the corruging tectonic zone, which is a very unusual beast in the Julian. It exposes mid-pressure granulate rocks over a wide area. So on the left here, this is a diagram that Tim has already shown. This is the time-space plot that we published in 2023. We now know that there are older rocks, Paleo-Archean to Meso-Archean rocks that are exposed in the Southwest terrain as well as in the UME terrain, as shown by these boxes that are outside of the diagram. And Tim has shown the old history that the UME preserves. It looks apparently that the Southwest terrain mainly lacks all this old history. From the Neo-Archean, there is at least a similar history of granite magmatism between the UME terrain and the Southwest terrain. And the two have been affected by what I will call the corruging tectonic zone tectonometamorphic event. And this was closely followed by cratonization at about 2600 MA. After that, in the Proterozoic, the Julian behaves brittly, largely. We see an emplacement of a series of dolerite suites in both the Southwest terrain and the UME terrain, and it behaves in its interior largely brittly, and we see only ductile shear zones affecting the margins of the craton after that. If we jumped on the other side of the Darling Fault into the Pinjarra orogen, you see that the ages of granite magmatism and metamorphism largely fall within the Neo-Proterozoic. And isotopic age data suggests that the basement to the Perth Basin is, as far as we know, up to 2.2 billion years old, so not underlined by the Julian Craton. I'll focus a bit more on the corruging tectonic zone. So in mapping, we can see that the corruging tectonic zone consists of southwest verging folds and thrusts, as well as sinistral strike slip shear zones. Another feature that we've identified is that the long axis of the lozenges in the northern UME terrain have been reorientated in a northwest orientation during deformation along the corruging tectonic zone. As a result, we interpret the corruging tectonic zone as a sinistral transpressive belt. I'm showing on this map also the metamorphic data points from our mineral history records. Here they are plotted by medium pressure. And you can see that this region here is covered quite homogeneously by green dots, which show these mid-pressure, about 6 kilobar rocks over really a wide area. And this is what's really unusual about this southern UME domain. This diagram here shows the summary of all these data points, and I'm showing here all the peak fields from all these points. We have supracrustal material that have been deposited at about 2.7 GA that preserve peak conditions of about 6 kilobars and above 800 degrees C. And the peak metamorphic ages are 2665 to 35. And these rocks must have exhumed before the emplacement of the 2615 Yandinilin dikes, which are unmetamorphosed and emplaced in the upper crust. These dikes are these thin red lines that you can see through here. They suture the boundary between the southwest terrain and the UNME terrain, and thus also provide an absolute minimum age for the structures of the corruging tectonic zone. During the mapping, we've subdivided the southwest Yilgarn into several domains, which was largely based on structural history, granite class metamorphic conditions. In the corruging tectonic zone is that domain in blue in the center of the map, which is a high strain, high metamorphic grade domain. Domain 1 would be the more typical UNME crust that has not been affected by the corruging tectonic zone event. Domain 2 is already high-grade metamorphic rocks, but not as deformed as the corruging tectonic zone. And then the seismic line will go into domain 5, 6, and 7 of the southwest terrain. The domain 5 is characterized by west-northwest striking shear zones that are Archean in age, as they are truncated by shear zones of the corruging tectonic zone. And domain 6 and 7 are variously reworked parts of the margin of the craton by the Albany-Fraser and Pinjarra orogen, respectively. All right, so these two cross sections here, A to B and C to D, are our pre-seismic data schematic interpretation for the corruging tectonic zone. We start in the east in a dome and key dome and basin sort of architecture in the UNME terrain, and we see that deformation strain increases towards the west, towards the terrain boundary. And we explain the exhumation of the mid-crustal rocks of the southern UNME terrain by a series of thrusts, southwest verging thrusts of the UNME crust over the southwest terrain, and it's accommodated in the east by normal faulting. So this is where the southwest one line will go across, and the southwest one line started in the east, in the Albany-Fraser, where it joins with the existing AF2 line. It goes across the Jada Cut-Up Fault into domain 1 of the UNME terrain, then into domain 2 once we go across the UNME shear zone in high-grade rocks, and then high-grade and highly deformed rocks of the corruging tectonic zone. We'll go over the boundary with the southwest terrain into domain 5, and then 6 and 7, over the Darling Fault into the Perth Basin, and eventually the Dunsborough Fault into the exposed rocks of the Pinjarra orogen in the Lewinian layer. So this is it. This is our preliminary interpretation for Southwest 1. In the next few slides, I will show more detailed views on the eastern, central, and western portions of the section for more detail. At that scale, we can see that the moho characteristic changes along the section. We can see a really sharp and well-defined moho in the east that becomes a bit more complicated and diffuse towards the central part of the map, and then eventually it gets really, really cryptic in the west and only controlled by a few reflectors. So this is the eastern part of the section where we start in the Albany-Fraser. So this is the Albany-Fraser 2 line and existing line. We see that the moho is well defined in the east, and in the and we start into this east dipping moderately to highly reflective mid-crust that was previously interpreted on the AF2 line as the Yarraquin seismic province. And progressively, we see the appearance of a weakly reflective lower crust, overlain by a highly reflective mid-crust. We do see as well these really strong structures, which are east deep low angle shear zones, and the upper crust is characterized by dome and basing architecture. In the central part of the section, again, we can see the moho quite clearly in the east, and it dips quite drastically in this region up to at least 45 kilometers depth. The terrain boundary, here we see a mid-crustal structure extending all the way through the crust and through here, and we see southwest verging folds and thrusts as well in the upper crust, and this thrusting is the explanation for the exhumation of the mid-pressure granulite rocks of the southern UNM terrain in the corriging tectonic zone. In domain 5, in the southwest terrain, we see a series of blind thrusts that affect a previous domain basin architecture through here, but mostly what we see here is this feature here, which is a lower crustal or mid-crustal ramp that along which this low reflectivity lower crust is thickened and duplicated in the same region as the moho bulge. So that's the western portion of the line where we see the transition of the Yilgarn craton into the Proterozoic crust. I will let Ivan and Charmaine talk about this portion in more detail. But for the Yilgarn part, we can still see the moho tracing through here, and then it becomes pretty fuzzy further to the west. The structures in this region, based on what we know from mapping, we know they are likely Archean shear zones that have been reactivated during the Proterozoic. And what is striking about Southwest 1 is this particular zone, this completely non-reflective lower crust. I will go back to that later in the talk. But first, I want to go back to the crustal root and stress how unique this feature is in the whole Yilgarn. And I've put here all the deep crustal seismic lines that we do have available for the Yilgarn craton, including all the UNM lines, the Midwest line that Tim's just talked about, as well as the Eastern Goldfield line and the Northern Yilgarn lines. And you can see that all of them have really very sharp mohos. This bulge in the Southwest 1 line is a unique feature to the southwest part of the Yilgarn craton, and we interpret this to be of Archean age. To go a bit further in the interpretation for this crustal root, from the gravity modeling that Sasha has done for us, we can see that this is a really dense material, so that's consistent with the homogeneous garnet-bearing mafic crust composition for this domain. And so we interpret the crustal root and this weakly reflective zone of Southwest 1 as genetically linked with the corriging tectonic zone event, and possibly as a residue of lower crustal anatexis of the Arakwin seismic province. And it was then thickened and duplicated along the mid-crustal ramp in the footwall of the CTZ. So the CTZ is a unique tectonic style in the Yilgarn craton in the sense that we have a widespread exhumation of mid-crustal rocks and a strong localization of deformation in a deformation belt, in a wide deformation belt. Although simplistic, I quite like these diagrams from Kanya et al. 2011, where they show the interrelationship between metamorphic conditions and strain localization. And they show at high to ultra high thermal gradients, the crust is very mushy. It's very hard to produce any localization of deformation. The deformation we see are dispersed dominantly strike slip shear zones across the whole terrain's width. At lower thermal gradients, we start to be able to create orogenic domains where thrusting can occur and crustal thickening can occur, and exhumation processes can start to occur as well. At even lower thermal gradients, we go into regions of really strong localization that is common in modern orogens. This diagram below, they posit that although we do have a secular change from gravity-driven tectonic in the Archean into the modern cold orogens in the Phanerozoic, there are periods within the Proterozoic where, in the same time span, different kind of orogen can occur. So indicating that the secular changes of mental temperature is not enough to explain the change in tectonic character, but also local processes are in play to dictate the tectonic processes. This is the same PT diagram that I've shown before. I've just stretched it so it fits the same scale as this diagram here. And you can see that our PT curve sits in between the two curves in through here. The architecture for the corriging tectonic zone resembles more that of a moderate localization panel through here. And so we broadly interpret the corriging tectonic zone as a transitional tectonic style between these Archean ultra-hot orogens and the Proterozoic mixed hot orogens. All right, is there any possible relationships to the Midwest 2 line? Well, we do see also a deep moho, as Tim has already shown. It is shown by a moderately reflective lower crust, and we have a highly reflective mid-crust that is duplicated along a thrust imbricate, and the upper crust is largely non-reflective apart from local greenstone packages. The thrust imbricate of Midwest 2 in through here, well, I wonder, we don't know if it's a Proterozoic as Tim suggested, or if it's related to the compressional event of the corriging tectonic zone. You can see that the thrust imbricate of Midwest 2 sitting through here in between this dashed red line and the thick red line, which is our area of exposed deep rocks of the southern UNM terrain. All right, so we've got very different tectonic styles that are preserved across the three lines. As Tim's already shown, the Midwest 1 line shows very different styles in the region where we've got dome and keel tectonics preserved at the surface, and very different as well from what we see in the distributed transgressional shear zone domain. And I would argue that the Midwest 2 and the Southwest 1 line again show a very different seismic character in a region where we do know that the tectonics, the tectonic style of the corriging tectonic zone is also very different. All right, so what happens further west? The modifications of the western Hilgard Craton's margin, we enter into this region of non-reflectivity crust. The question is, and we did wonder during all this process, is this an Archean modification, Proterozoic and Phanerozoic modification of Archean crust, resulting in this non-reflective zone at all? Or is this a whole Pinjara orogen Proterozoic crust under thrust underneath the Hilgard? Well, I don't know. At the moment, we do not exactly know the answer to that, and perhaps we'll never know, but we do have some methods that can help. We do see, and Sasha will talk a lot more about this afternoon, that this non-reflectivity zone match and fits exactly where we do have a big conductor in the upper crust, in the lower crust, and in the upper mantle. And maybe we do have now also a mean to probe the mid-crust, looking at the mafic dikes that are prevalent everywhere into the southwest. And I'll just show here the results from Kirkland et al.'s paper, where he sampled a Proterozoic dike just right by the Darling Fault, just right above this non-reflectivity zone. This dike was assigned to one of the 1390 dike suite in the region. And looking at xenocrysts components within the dike, it managed to date a zircon grain that was an inclusion within a titanite grain, and the zircon grain itself preserved an age of 3.4 GA. Not only that, they've dated as many minerals as possible, And they found another two Concord-occutant zircon ages at 1.6 and 1.4 GA. They've also dated titanite, which showed the effects of the thermal overprints of the Pinjarra orogeny on this margin, and the apatite showed even younger denudation processes. So this is probably a good mean to try and understand better all these unexposed seismic provinces. And I'll leave it there. Thank you.